Alright, hell yeah. So it's so important to check your work when doing anything in math. You know what I mean? We're going to take a derivative of this equation. So in this video, we're going to check if the derivative of this equation, which is this, if it's correct. And we're going to graph both. So I have this one in blue, this one in red. And so we're going to figure out if they're correct by graphing both equations. We're going to choose an x value for this one, because that's going to be well, and then we're going to use a solver for this. We're going to find the slope using a solver, and then we're going to compare it to the value of this equation. So we're going to come to the blue equation, and then we're going to 6 is the derivative, and it finds the slope at that point. So it's 0.1124. Now I'm going to go find the value of the red line at that same x value, and it's 0.1124. So hey, we're good there. We can even try it a different point. So this is the derivative, 0.196, and then we'll go to the red graph, and that y value is 0.196. Okay, hell yeah. Now we're going to find the derivative of this equation using both the product rule, which is way easier to memorize than the quotient rule. So the product rule just says the first times the derivative of the second plus the second times the derivative of the first. Even if you have the product of three things, it's still fairly straightforward. Three or more. You know what I mean? It's going to be the first two times the derivative of that one. Okay, and then maybe the second one is the derivative of this. So these two times the derivative of that, plus, and then you're going to do this one. These two times the derivative of that. You know what I mean? And so, hell yeah. Alright, so that's the product rule. The quotient rule says it's low d high minus high d low, all divided by the square of what's below. So that's what I have right here. Low d high minus high d low, all divided by the square of what's below. But you might miss this minus sign, and I don't know, you might do high, did I even get this right? High d low, low d high minus high d low. So yeah, I even probably wrote it wrong. So even just right there, that's the whole reason why we're going to check it during the product rule. Yeah, I think it's high d low minus, yeah, so that's fascinating. I think I have an error here. You know what I mean? Double check. But that's where, at the end of the day, use the product rule, because it's going to be less likely to make errors. Okay, so we're going to do the quotient rule first. And I did it. It is low d high. So how the hell are you going to memorize that? So even if this one is correct, how are you going to memorize whether it's low d high or high d low first? Because you do have a minus sign, so the order matters. And I have no idea. You know what I mean? Okay, hell yeah. But let's go through this. So we have the lower portion, 3x plus 4, times the derivative of this upper portion, which is just 4, minus the upper portion, high, multiplied by the derivative of the lower portion, which is 3. So low d high minus high d low, all divided by the square of what's below. Okay, hell yeah, we're going to FOIL this through. So we have 12x plus 16. This is going to be subtract. We're going to do this first. We have 12x minus 9. And then we're going to FOIL this negative, minus 12x plus 9. And now we have the 12x's cancel. 16 and 9 becomes 25. Okay, hell yeah. So I think that looked pretty good. And now we can use the product rule to double check. And so how do you use the product rule when you have a quotient? Well, just bring whatever's downstairs upstairs by having it to the power of a negative 1. Alright, if you do this, then you can just use the product rule. And so the product rule is going to be the first times the derivative of the second. So how do we take the derivative of this? You bring down the power, and then you take whatever's in parentheses, 2, and then you reduce the power by 1. Cool. And then you have to multiply by the derivative of what's inside. That's going to be 3. Cool. So that was this times the derivative of that. Now we're going to do plus the second, that's what I do, times the derivative of this, which is just 4. And scene. We're done. You know what I mean? Now, how does this end up being like that? Well, maybe, and it does, but this is a little bit uglier. That's probably why you'd want to use the quotient rule. But all this portion is just, hey, that's downstairs squared, and hey, that's half the battle. This is downstairs just to the 1 power, and so so let's do this. So this is going to be, I foiled through the negative 4x plus 3, and then I did times 3, and then we divide by 3x plus 4 squared. Hell yeah, this side is a 4 up top, and then 3x plus 4. Now, to add these fractions, I need the denominators to be the same. So I'm going to multiply this by a 3x plus 4 top and bottom. So now the denominators will be a 3x plus 4 squared. Foil this, we have 12x plus 16. Hey, now we're cooking. The 12x's, and then foil this, we're going to have negative 12 plus 9. The 12x's cancel. The 9 and 16 become 25. And hell yeah. So product rule and quotient rule give you the same answer. And I love stuff like this because you can always double check your work. If you're using the product rule, double check it with the quotient rule. If you're using the quotient rule, double check with the product rule. And mainly if you have something that you could use the quotient rule on, maybe you forgot, how it was. And it's, I guess it's low d high. Hell yeah. So it is low d high minus high d low, all divided by the square of what's below. Okay, hell yeah. So now we're going to see. So we turned this into, we had this function, and this is in the section of, James Stewart calculus. I'm trying to learn multivariable calculus, and they started with sequences. So that's kind of the chapter that we're doing. And so if this is a sequence where n is integers from 1, 2, 3, so forth and so on to infinity, we need to determine if it is increasing or decreasing on the interval for all values of n, when n is positive integers 1 to infinity. And I'm going to do this more. Anytime that you use kind of a mathematical symbol, an arrow, and then an infinity, write out how you would say it. This is 1 to infinity. Now you might be able to say things in different ways, but hell yeah. And so what we do to see if this is increasing or decreasing as n goes to infinity, or for all values of n, is it increasing or decreasing for all values of n as n goes from 1 to infinity? We need to represent this sequence as a function. That's easy enough because we can just put a value of x in there. So let's say you had a sequence, an is equal to x. I'm sorry. Very simple. What if you had a sequence that says an is equal to n? When you're doing sequences, it's hard to relate this to y equals x, but this is what it would be like. This would be y is equal to x. The sequence, we all know what y equals x is. That's just that. 1, 1, point, 2, 2, point. I'm going to throw an x value of 2, and then that's my input. My output is a y value of 2. So this is the yx. So now, what does a sequence do? Well, a sequence says, hey, we're not going to have 0, but we're going to start at n is equal to 1, n is equal to 2, and let's do up to n is equal to 3. And then so we're going to say, hey, that value is going to be 1. When n is equal to 1, the value is 1. When n is equal to 2, the value is 2. N equals 3, the value is 3. So this is what happens when we have a sequence. We just have individual points, even though if you put them together, you know what I mean, it would look, if you had this actually representing infinity and you had to draw it, you would have a graph that looked like that. If this, because all your points would be so close together. But hell yeah. A sequence just has individual points, and so we represent it as a function where a function can be any value in between. Hell yeah. once we have this represented as a function, then we can find the derivative of this function, and we can determine if this derivative is increasing or decreasing on the interval where x is greater than 0 or 0 to infinity. Any value of x that is greater than 0, and all values of x from 0 to positive infinity. All right, so let's do that. So here is our sequence. It's 4n minus 3 and 3n divided by 3n plus 4. Change it into a function just by replacing n with x. And then we're going to take the derivative of this. You know what I mean? Low d high minus high d low, all divided by the square of what's below. FOIL, simplify. We've already done that. 25 divided by 3x plus 4 squared. So let's see what we do. X is always a positive value from 0 to positive infinity. So that's kind of the first point. You know, if our values are always positive, 0 to positive infinity, because our n values are going to be integers, 1, 2, 3, all the way up to infinity. And so, so that's a start that, hey, this thing is going to be, so this is our check 1. Hey, it's going to be always, and this is representing the slope. So this is the slope. You know, check 1 is always going to be positive. I don't know, maybe there's a negative here that makes everything negative. Then, you know what I mean? So let's go to the next one. Nothing makes it a negative value in this equation. Cool. So if I put in this 3, doesn't make anything negative. Adding 4 doesn't, you know, it's not subtracting, so it's always going to be, you know, more positive. And then a square. Even if it was negative, that square is going to, you know, turn it into a positive. But we're already starting with a positive, squaring it. We do get a positive. 25 divided by that. There's nothing here that makes it a negative. So furthermore, all values of x from negative infinity to infinity, even though the sequence just wants values 1 to infinity, I mean, it is obvious here to be like, hey, if we had, for this function, even if we go the other direction and put in negative infinity, we're squaring that. And so, because I was thinking, well, this, we might put in values that are negative that actually make this negative, you know. Any large negative value makes this part negative, but once we square it, it's always going to be positive. So furthermore, all values of x from negative infinity to infinity will yield, or the output will be a positive value. It'll generate a positive value for the derivative. So therefore, we represented this sequence as a function. We know the rules of derivations to find this is an equation that represents the slope. So back to this is if, let's trace this out. If the red line represents the slope, this red line represents the slope of the blue line. So you see how this blue line has a real big positive slope? Okay, so let's see what this value says. The value of the red line says 5.2. So this value of this derivative says 5.2. Guess what? That's the slope. And then where the x value, where x is negative 0.6, negative 0.6. So we're going to throw in an x value of negative 0.6 here. And so at an x value of 0.6, the slope is 5.2. That's what this equation says. And so, So then if I go to this equation where x is equal to negative 0.6 and use the solver function on my calculator to find dy dx, or the slope of that. So I'm going to trace this out. So now we're on the blue function, and I'm going to use the solver to find the slope, and the slope says it's 5.25. So that is a check right there. Okay, so we're done with this video. But I just thought, I'm glad we started with the graph and ended with the graph of being like, hey, if you're using math to get an equation, check to see if it even works. And starting with an original equation, you can put it into a calculator and find the slopes. So again, we're going to do that. We're going to, the blue is this, so this slope is going to be pretty small. and we're going to find the slope right there. So at an x value of 6, the slope is 0.05. So now we're going to go to this equation and put in that same x value of like basically 6, and the output says it's 0.05. So the output of this is the slope. So at the x value of 6 in this equation, the slope of this equation is 0.05. And then so we're going to say when the x value is 6 in this equation, it outputs that number 0.05 for that slope. Okay, we're done with this. Thanks for joining me. Hell yeah.